I want to deal with this tape. This is going to be a short one about structural equation modeling, the statistics procedure, and natural selection as a fitness optimizer. There's, the only difference between chemistry and biology, and therefore the explanation of everything in living systems, is natural selection. So it's the entire content of biology. It's generated brilliant systems, and it really has achieved systems like parts of visual eye detection, eyes in visual systems of animals that are operating at the physics maximum level, even though natural selection does not seek or force that optimum level. But over eons, it's drifted to that optimum level, the physics optimum possible of a system. In many cases, we've discovered that. It's been published in Nature magazine in the last 3 or 4 years. So optimizing fitness is not primarily what natural selection does, but the end result of natural selection being there for eons is a drift in many subsystems to the optimum. It's not driven by natural selection itself. And then this is like the hit song research that was done, where they looked at hundreds of hit songs in all kinds of markets and all kinds of genres, and they found it was path-dependent luck. That experts in the field, and this is experts in, disco dancing, not experts in some stupid new school of music, experts in every genre of music on the street and hip-hop, whatever, those guys, those ladies, they said that the number 200 song and the number 1 song and the number 202 song and the number 2 song were in no musical way different or better. They were the same quality. And one of them made $100 million and one of them made nothing. And so the research on hit music was really well done statistically and really indicated that luck is 99% of it. Natural selection's drift to optimum, according to Kimura, is much the same. It's a drift until luck hits. If you can hang around for 1,000,000 years of random variation, luck's going to hit you and move you to a physical optimum. Now, there's so much about natural selection that has strong analogies of just simple statistics. And I want to lay out a couple of them right now. One of them is the structural equation modeling, which is this silly thing where you have do from I equals 1 to 100. So when computer programs came, we could do not one correlation, but we could do multiple correlations. So do a correlation from I equals 1 to 100 with different data points, and that would get you multiple correlations. So this variable with that variable, this variable with this other variable, this variable with this other variable. That was just do from variable 1 to variable 100, correlations between all these variables. So you had multiple correlation software in SPSS and all these big systems and SAS. That was a big deal for 15 years in academia. Then you got Tetrad from Carnegie Mellon, where you had doing multiple correlations. Do multiple correlations from I equals 1 to 100 with every possible combination of variable in the system. Just without any theory, looking for significant correlations and patterns, and then asking if there's any meaning to this after you find them. Now, this is a real violation of what good science and social science is supposed to be. But the Defense Department really liked it, put billions of dollars behind it for terrorist pattern finding, and it worked. They found patterns that had no meaning for a while, and then they found a framework that made those patterns very meaningful, saved lives. So, but structural equation modeling, if you optimize the parameters so that your model fit, and in structural equation modeling, you have 3 or 4 models of a phenomena. You let them compete statistically through multiple regressions for each, and then you see which one fits the best. And that you can tweak a model to make it fit a little bit better. The better it fits the actual data set, the more scientifically useless it is. In other words, the better it explains the current data that it's built from, the less it explains any other data set you apply it to. And there's just this paradox where if the pattern that I see for this data is really strong and clear to me, then everywhere else I apply it, I'm a bigot. Isn't that cool? That's so much like people. And then there's this other thing, the University of British Columbia, Vancouver. Totally different stuff now. I'm going to leave that. Remember, that's like natural selection. If you make a model in terms of genes, the code in an animal optimal for a present environment, then it kills, it fails to adapt. It's a suicide. If the animal is really, really fit for the present environment, if the present environment has big sudden shifts instead of slow gradual shifts, the animal dies because it's too optimized for the local data set. So that's the analogy with structural equation modeling and natural selection fitness. Now let's look at another entirely different entity, but related also from statistics, where this wonderful genius at the University of British Columbia, Vancouver, I can't remember his name, has this book he wrote maybe 10 years ago that I bought it, and it sounded really clever, and I attempted to read it 6 or 8 times and couldn't quite get around to reading it. And finally I read it clearly, and I was just amazed with and understood why I had originally picked it up. There's this one amazing idea, and he just looked at the neural net computer things where you make a little network of nodes, and you have some sensors that sense something, and then you have these nodes that look for patterns among the sensation uh, input nodes, and then you output what you think you're sensing. You could optimize, get a network optimized to recognize the letter R, or to recognize the name Richard Green, or to recognize the shape of a particular terrorist head in airport video camera, something like that. You train it with thousands of examples, train the network until it optimizes the weights it gives to these various nodes among the input sensors. Uh, the pattern of weights among the nodes. This node is a 21, more powerful than this one, which is a 2. This one's a 7. So you optimize the pattern of weighting among the nodes that maps these various patterns of inputs to let you know when a pattern of inputs is that face. So you're looking for that face as a pattern among noisy inputs. And you do training to teach the network how to recognize that face. And then once the network's trained, it's got the relative distribution of weights to do that. And then this guy, British Columbia, said, I wonder, this is totally different than AI rule bases, which tried to do the same thing, but you had to have the rules up front, and unless they were really primitive, and then you had to look at the control rules about when you use some of those lower level rules. And that was sort of the equivalent of these correlational weights among a neural net. And then he applied statistics to these weights. And he was able to turn the neural net weighting patterns into AI type rules that made sense in terms of entities and ideas. And he found out that the rules that the neural net trained with 1,000 or 100,000 examples developed on its own as a machine, not human done rules, differed from human rules in a fundamental architectural difference. The human rule sets tended to be uniform at different size scales. So you had a few big general rules and a few medium rules and a few very, very specific rules. And it's sort of branched out in a tree-like way, but not hugely branched out. Whereas the neural net developed rules consisted of anchors, these 10 or 15 gigantically deep and specific rules that are far more detailed than any humans would have come up with. And then these little tiny, highly general, giant population of highly general rules. So it was both deeper than the human rules and more general than the human rules, and lacked that sort of intermediate layer that the humans had. And remember, a neural net machine has no biases because it's not a human and hasn't been raised by parents in a society. And it just looks at things that change when other things change, whatever they be. And humans can't do that because we have opinions about what should change. We have these causal intuitions our mommy gave us and our society gave us that make us biased. And these neural net things don't have that, and they come up with this. And so that raises questions about the role of bias and the danger of bias in all human thought, and the extent to which all of society is just created biases of a certain sort. Ruts, you could call it, as a positive thing or as a negative thing. And then natural selection does natural selection too generate highly general entities and anchor extraordinarily optimized entities, and the strange mix out of middle? Don't know. Don't have any data on that, and don't know what level of analysis you would look at that. But there are these analogies between natural selection and statistical processes. that have some deep connection in that everything in your mind and everything in all of human culture and civilization is created by factor analysis, because that's just what changes when this changes. That's all factor analysis is, all it measures. And that's all neural net computers do. And apparently everything in the human mind and human culture and civilization, we learn now, as babies, we learn natural language, blah, 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 blah. Everything in that we consider human and sophisticated and thought and complicated comes from watching what correlates. They have that wonderful lady at Harvard University who studies the child as scientist theory, they call it, where she has kids that, little tiny kids that see a block go behind a whiteboard and then see two blocks come out the other side. And they don't believe one block can, they already have a causal intuition that one block can't be born into two because it's a physical thing. And they want to look behind the board to see the cheating. And they start to crawl behind the board, and then they interrupt with lunch or something that totally wipes out this experiment so the child can't complete it. And then an hour later after lunch, they leave the child alone in the room with the whiteboard and the person and the blocks, and the child crawls behind the board to complete the experiment. The child remembers the incompleted experiment they were doing in their head and completes it. We are so statistical even at the age of 2 or 3.